Okay, so now to make this interesting is we take the derivative with respect to time. Right? So we determined that the position of Hal in my frame is the position of Hal in MD's frame plus the position of MD in my frame. So just take a derivative. Right? Then the velocity of Hal in my frame is the velocity of Hal in MD's frame plus the velocity of MD in my frame. It's the exact same rule. The exact same pattern is also true. Because all we do is take a derivative. What's the derivative? If Hal is moving in my frame, the derivative would be the velocity. If Hal's moving in her frame, the velocity. If she's moving in mine, the velocity. So you take the derivative of all three, it still has to be true. Right? So this really is the Galilean transformation, the idea that velocities transform like this. Okay? I was showing it to you first in position because that was what was going to make it really clear. So it didn't really happen. Okay? Usually you go straight to this. Okay? It also works for acceleration, but that gets really complicated. So you're just going to have to deal with it in terms of velocity. So what is he talking about? How do we use this? Let's do a quick problem with this. Okay, or let me see what questions have come up. I may just ignore them because I was all confused. Yeah. That's right. Okay, none of these are about my class. Okay. So the kind of a problem you'll do here. So let's write out a whole problem. This is so important here. I'm going to use this board. Oh, no. Yeah. Let's see. The kinds of problems you do are almost always about boats crossing a river or things flying in the air. Okay? So this is a case where you got to be able to read that problem and see the context to figure it out. Okay? So when a boat moves in water, okay, or an airplane in the air, I won't write that part. It moves in the water's reference frame. This is how we use this for problems. Or there are other things we can do. Okay? So let's look at just a quick example of how this works. So a boat travels 3 meters per second across a river moving at 2 meters per second. So let's think about that real quick. We have a river, and it's moving. The V of the water is 2 meters per second. Pretty fast. And you have a boat here that thinks it's moving at 3 meters per second. Now, just your intuition tells you what's going to happen, right? The boat thinks it's puttering along at 3 meters per second, but you're watching it, and you know what it's really doing. It's going like this, right? If you start here, and you're standing here, and your friend is here, and they try to go straight across the river, they're really going to drift because they're in the frame of the water. So hopefully, intuition-wise, you kind of see what I mean there. Okay? So now what we're going to do is apply all those vector rules that we just did and see if it makes sense. So let's draw it again here with a little bit of room. Here. So here it is. Here's the boat. So this vector, that is the boat, how it thinks it's moving. The boat always moves in the water's frame. So this is V of the boat in the water. Right? And then what else do we know? We know, let's see, the water is moving this way. Well, that's V of the water, but in what frame? Whose frame is that? So this problem might ask, how far does the boat drift across before, by the time, how far does the boat drift this way to go across? And then you got to read the problem and figure out, there's one more frame. Whose frame is it? It's the person standing over here, confused in physics class. Right? Like, what the hell is he talking about? It's the ground. Okay, I'll call it the ground frame. We'll call it the ground. Let's call it what I did in my notes, the land frame. This is the land frame. So in most problems, there'll be a third frame. They won't name it, but it's just you. It's just watching. Sometimes it's called the lab frame or the building frame. So this is the velocity of the water in the lab frame. Okay? When somebody tells you how fast a river is rushing, what do you assume they mean with respect to? Somebody standing there watching the water rushing. So there's that and there's that. So you could say, well, I want then, if I got to answer this question, to answer the question that I didn't state, you need what? You need the velocity of the boat in the land frame. Okay? Because you want to know how's it moving. If you have these kinematics, then you can figure out takes this long to cross, and in that time it drifts this long, right? So somehow you got to put these three things together. So how do you do it? You say, I want this. I want V, B, L. I want the velocity of the boat in the land frame. Don't even going to look yet. Don't even think. Don't look at the problem. Don't read anything. Just write V, B dash something plus V something dash B. Right? I'm sorry, dash L. Sorry. Right? That's how the rule works. B to something, something to L. And you say, do I know these? Oh, it's the water. I have the water boat in the water frame plus the water in the land frame. So it turns out they gave me exactly what I needed, right, to solve the problem. Okay? And this is how all the little components will go together. For example, in this problem, the question might have been, how fast is it moving in the land frame? Like, how fast is this boat actually going? And of course, by actually, we mean the land frame. There's really nothing universally important about the land frame, but that's what we usually mean in a problem. And you say, okay, well, I could write that. I could even write that in Cartesian coordinates. I could even write that out in Cartesian, because I could say, okay, it's this plus this. Let's practice our vector notation here. If we say this is y, and this is x, and this is all Cartesian, then what is the horizontal component? So they're already broken into components here, right? So your horizontal is strictly from the water and the land frame, the way I drew it. And it was water and the land frame 2 meters per second. So it'd be 2 meters per second I hat. Oh, those are rearing their ugly heads again, right? I hat. And then what is its y component? Well, that's entirely coming from the boat. What the boat thinks it's moving with, or what the boat is moving with respect to the water. All right, so that's up, I think I called that 3. All right, plus 3 meters per second j hat. Just means the x component and the y component. And I promised you that at the end the problem would say, well, what is, or convert back to polar. And this is the case. We have to convert back to polar because they want to know how fast is it moving. They want the total velocity. They want the speed. Right? They want the magnitude of the velocity. So if we have that, then we say the magnitude of the boat in the land frame, how fast it's going, independent of axes, just how fast it's going. Oh, it's Pythagorean. 2 squared plus 3 squared, whatever that is. The square root of 13 meters per second. Okay. So this is a case where it was kind of straightforward. Without going through this formality, you might have said, well, it sounds like a right triangle, doesn't it? Because we have one component here and one component there, so it must be that. That's really all you had to do. The boat, the water, together they make this. But when problems start moving in 3 dimensions and things aren't perpendicular, it can get a little more confusing, and this is formally how you get it. Okay?